as you see, applying temperature and speed correction to deflection measurements from traffic speed deflectometer. My name is Arman Hamidi. I want to briefly introduce myself. I'm a postdoctoral research fellow at Tampere University and also a pavement research engineer at ROADEX scanners. I have a PhD in road and pavement engineering from NTNU in Norway, and my dissertation was focused on analyzing data from traffic speed deflection devices. I also have a background in asphalt materials by having a master's degree from Sharif University of Technology in Iran. In this presentation, I will first talk about the mechanical response of a material and how it is relevant to the structural evaluation of pavements. Then I will explain falling weight deflectometer and traffic speed deflection devices that are used for this purpose. And notably, I will explain the measurement principle in traffic speed deflectometer or TSD. Then I will explain how temperature and speed affects these responses from these devices. So I need to briefly talk about the viscoelastic behavior of asphalt mixtures and also the importance of this temperature and correction adjustment. And finally, I will explain how to develop correction factors, temperature correction for FWD deflections, and also temperature and speed correction for TSD measurements. If you consider these three-point flexural tests, we can apply a load with a known value to a material. And if the dimensions of the material are known and the load is known, using this test, we can measure the response in sort of displacement or maximum displacement. So if we use an equation like this, we can relate this displacement with the load, dimensions, and a parameter related to the stiffness in the material, which is elastic modulus here. So we apply the load and we measure the response. We have dimensions, and by relating them, we can determine material properties. This simple principle forms the basis of pavement structural evaluation methods. But how road materials are evaluated? When we deal with asphalt pavements or flexible pavements, we can test asphalt mixtures. For example, in the laboratory, we can use 4-point flexural test, SCB test, and ITS test for investigating the potential to fatty cracks. We can also use wheel track test for rotting. We can use dynamic modulus, resilient modulus, and other tests. We can also separately test the components of the asphalt mixtures. For example, we can perform CBR or triaxial test on granular materials, or we can test the bitumen separately using some classic tests such as ring and ball and penetration and so on, or using some more advanced tests such as BBR and DSR. And when we're dealing with concrete pavements or rigid pavements, then we need to test the concrete using, for example, compressive strength or flexural strength tests. But in the field, it is not feasible to use these tests. We can extract cores from the field and go to the laboratory and perform laboratory tests on those cores. But again, this procedure is not feasible at network level. So in the field and at network level, we need to use non-destructive tests, including ground penetrating radar or GPR that is in use for determining pavement layer thicknesses and also to detect the moisture susceptibility in some pavement layers, and also deflection measurement devices, including FWD and TSDDs. FWD, or falling weight deflectometer, is the standard device for structural evaluation of pavements. It applies an impact load to the pavement surface. The load level is controlled, and there are different radial different sensors at different radial distances that mounted on a beam. So these sensors measure the response in sort of deflection. So we will have a shape like this known as deflection basin or deflection bowl. There are two general approaches for analyzing data from FWD. First is using deflection basin parameters or DBPs such as SCI, SCI 200, SCI 300, BCI, and so on. These parameters provide an initial understanding of the structural integrity of the pavement structures. For example, SCI 200 is believed to be related to mode 1 rotting, or BCI is believed to be related to the structural integrity in sublayers. And the second method for analyzing FWD data is using back calculation tools for determining elastic moduli of pavement layers. In this regard, we can remember again that the flexural bending test, we have a known load, and we also have dimensions of the material, that is pavement layer thicknesses here. So we can determine these using GPR, and we have a response, which is not a single value, more complicated, but by relating the load, dimensions, and the response using a software tool, we can estimate the elastic moduli of pavement layers. Although FWD can provide pretty accurate measurements, it has several limitations. For example, when FWD operates, the lane must be closed to traffic. So there might be safety concerns regarding both the road users and also the operators. Number two, it provides discrete measurements, so there are gaps in coverage. When we use FWD to measure one point, and then we want to go to the next point, the vehicle must move to the second point, and there is an interval between these measurement points, and this interval is typically 25 meter or 50 meter. So if any structural distress exists between two measurement points, FWD cannot detect it. Number three, FWD uses an impact load to model traffic load, but we know that traffic load is induced by vehicles, but by vehicle tires, and it is not an impact load, it is a continuous load. And finally, FWD is slow in operation, so it is not suitable for network level evaluations. Due to these reasons, traffic speed deflection devices, or TSDDs, were introduced. These devices provide continuous measurements. They can measure at traffic speed, and as they apply the load through vehicle tires of a heavy vehicle, so they can better resemble the service condition of roads. And finally, they are fast and produce huge amounts of data, so they have potential to be used for network level evaluations. Currently used type of TSDDs include Traffic Speed Deflectometer, or TSD, Rapid Pavement Tester, or Raptor, and Measure Deflectometer. In TSD and Raptor, there is a measuring beam inside the trailer of a truck, but a Measure Deflectometer is a standalone beam that can be mounted on a user-specified vehicle. Traffic Speed Deflectometer, or TSD, is the most widely used type of TSDDs at the moment. It is developed in Denmark as of 2004, and there are 23 units built to date. TSD is an articulated truck with 3 axles, and it applies a load around 100 kilonewton through its rear axle. So the pavement is deflected under the load, and there are Doppler laser sensors on a measuring beam, and the beam is located on the right-hand side of the vehicle between twin tires. In the newest generations of TSD, there are 10 Doppler laser sensors, 3 of them behind the rear axle and 7 of them ahead of the rear axle, plus 1 reference sensor. And the TSD does not measure deflection. It measures deflection speed or deflection velocity. But by dividing deflection velocity by the horizontal speed of the vehicle, we can determine deflection slope. These deflection slopes can later be converted to deflections using deflection algorithms. And these deflection algorithms work based on curve fitting and then integration. One important point regarding analysis of TSD data is that unlike FWD, at which the maximum deflection occurs below the maximum load, in TSD, the maximum deflection occurs behind the maximum load, and there is the lag distance between these two. This lag distance is called viscose lag and is believed to be affected by some parameters, including the viscoelastic characteristics of the asphalt layer. But how temperature and speed affect measurements from TSD and FWD? If we come back to these 3-point flexural tests, when temperature is high, we expect to have higher deflections. When temperature decreases, we expect to have lower deflections. When the loading speed increases, so the load duration would be shorter, so we will have lower deflections. And when the loading speed decreases, so we will have longer load duration and therefore higher deflections. So we can say that the effect of temperature and speed is mostly reflected in the modulus. When temperature is high or speed is low, we will have lower values of modulus, therefore higher values of displacement or deflection. So if we want to investigate how temperature and speed affect deflection measurements, we need to know how temperature and speed affect modulus. But asphalt mixtures are not elastic materials. They are viscoelastic materials. And if I want to simply explain it, when we apply a sinusoidal load to an elastic material, we have stress and strain curves, and there is a distance, a lag distance between maximum stress and strain. But in a purely elastic material, this lag distance known as phase angle is 0. When this phase angle increases to 90, then the viscose behavior will dominate. So in a purely viscose material, this lag distance is 90 degrees. And in a viscoelastic material, it is typically between 5 to 45 degrees. So for viscoelastic materials, we cannot use a simple elastic modulus to describe the behavior, but we need to separate the elastic behavior and viscose behavior. So instead of using elastic modulus, we need to use complex modulus. And two components of this complex modulus are E prime and E double prime, which are storage modulus and loss modulus. Storage modulus reflects the elastic part, the elastic component of this complex modulus, and E double prime reflects the viscose component of the modulus. And the magnitude of this complex modulus is called dynamic modulus. But how in the laboratory can we determine this dynamic modulus for different asphalt mixtures? There is a separate test for it. And in these tests, sinusoidal loads are applied at different temperature and speed levels, and modulus is measured for each temperature and speed level. As many modulus values will be produced to facilitate the representation of this modulus, this parameter known as reduced frequency is defined. Reduced frequency combines the effect of temperature and speed. So instead of showing different modulus values at different temperatures and then different speeds, modulus values are shown at different reduced frequency values on a curve like this. And the curve is called dynamic modulus master curve. So for each asphalt mixture, a separate master curve can be obtained. So this is regarding the representation, but how about the model? How about the equation that can be used to describe this dynamic modulus? There are different models that are used for describing the viscoelastic behavior, and one of the most famous one of them that is believed to be suitable for describing the linear viscoelastic behavior of asphalt mixtures is the Huet-Saillet model. The model is complicated. There are different parameters in it. And the two important parameters that I want to mention are T, which is temperature, and omega, which is angular frequency, and it is related to speed. So if we use this equation for complex modulus, we can better understand how changing temperature and also speed will affect modulus, and it will then affect the responses from deflection devices. But as we see in this equation, this is a real number. There is an imaginary unit. So we cannot use this E star in a traditional forward calculation or back calculation tools. So we need to determine the magnitude of complex modulus. If we define two parameters, M and N, then we can separate the elastic and viscous parts. So we can write this E star as the combination of these two components. So this component is the part without imaginary unit is the storage modulus, and this part is the loss modulus. Now that we can determine storage and loss modulus, we can use this equation to determine dynamic modulus, which is the magnitude of complex modulus. But to understand this better, I have provided a numerical example. So for a typical asphalt mixture with these model parameters for the Huet-Saillet model, if we increase the temperature from 0 to 40 degrees of centigrade, we can see in this table how dynamic modulus will change. So for this specific asphalt mixture at 0 degrees of centigrade, dynamic modulus is around 16,000 megapascal. And for the same mixture at 40 degrees of centigrade, the dynamic modulus is 948 megapascal. So we can see numerically how increasing temperature will decrease dynamic modulus values. And the same can be shown for the vehicle speed, how increasing vehicle speed will increase dynamic modulus. If we model TSD load from multi-axles of a TSD vehicle on a pavement analysis software that is capable of modeling the moving load, such as 3D move analysis or viscoroutes. And I used here viscoroute, which is a French software. And we develop a typical pavement structure. We define the properties of a certain pavement structure and model the TSD load. We can see that by increasing temperature from 0 to 40 degrees of centigrade, how these deflection values will change. As it is shown, by increasing temperature, deflection values will increase. And this increment is more pronounced at inner radial distances than outer radial distances. The main reason is that in the modeling, only the surface layer shows viscoelastic behavior. And in FWD deflection basin and deflection basin from a measurement device, the inner part of the deflection basin is more related to the characteristics of the upper layers. So this part is showing the characteristics of the surface layer, and this part is showing the characteristics of the sublayers. So as the asphalt layer was defined viscoelastic, we see that this temperature will affect modulus values from the asphalt layer, which is shown at inner radial distances. And if we increase vehicle speed from 10 km per hour to 110 km per hour, we see that by increasing vehicle speed, we will have lower deflection values. And again, the effect is less pronounced at outer radial distances. But compared to temperature effect, at outer radial distances, there is a minor effect. But here, the effect of speed variation on deflection values at outer radial distances is almost negligible. And in comparison between temperature effect and speed effect, we can say that in general, temperature has a more pronounced effect on deflection values, but both temperature and speed affect deflections. And also, if we look at this curve on the right, we see that by increasing speed from 60 to 110 kilometers per hour, the effect of changing speed on deflection values is almost negligible. So speed variation is more important at low speed levels, and at high speed levels, the effect of speed on deflection values is almost negligible. So temperature and speed affect deflection measurements. But at network level, what is the importance of correcting these effects? Why do we need to correct the effect of temperature and speed variations? Consider this curve of SCI 200 for a road section in the Finnish road network. SCI 200 is believed to be related to mode 1 routing. So when SCI 200 increases, the potential of mode 1 routing increases. If we consider these 3 points that were specified using these circles, if we do not correct the effect of temperature and speed, for these points, SCI 200 is 300 micrometer. If we do not correct temperature and speed, we treat these points similarly. So we will think that the potential of mode 1 routing in all of these pavement sections is equal. But if we correct the effect of temperature, for example, to 20 degrees of centigrade, as the temperature during measurements is different in these 3 points. If we correct the temperature to, for example, 20 degrees of centigrade, then this point will not change. But this point that was measured in 30 degrees of centigrade will go down. And also the same happens to this point. So the corrected SCI 200 values for these 2 points will be lower than this third point. So without correction, we will treat them similarly, but after correction, we will know that this point is, this pavement section is more prone to mode 1 routing. In other words, without temperature correction, we may misinterpret the TSD data, and it will lead to incorrect conclusion about pavement performance. Also, when we have measurements for one road section at different times, for example, here, again, SCI 200 for a road section in the Finnish road network in 2015 and 2020, we see that there is not any significant change in the values of SCI 200. So no deterioration over time can be detected. But if we check temperature profiles during measurements, and these are surface temperature, we see that during 2015 measurements, temperature is around 20 degrees of centigrade, and during 2020 measurements, it is around 10 degrees of centigrade. So if we correct measurements to, for example, 10 degrees of centigrade, so this green curve will remain at the same place, but if we correct to 10, this red curve will go down. So 2015 measurements will be placed below the 2020 curve, and we might be able to relate the difference in SCI 200 to deterioration over time. To put it briefly, temperature and speed correction is necessary when analyzing data from TSD and also FWD. For FWD, we have temperature correction. For TSD, we need to apply temperature and speed correction. If we do not apply temperature and speed correction, variations in TSD data may be misinterpreted as structural differences rather than the result of change in material stiffness due to variations in temperature and speed. So now that we know it is important to correct these effects, how can we do that? I start with correcting temperature for FWD, and then we'll expand it to correction on TSD, because the principle is almost the same. For FWD, we use 2 software tools, CanLayer and vScrew. So at road scanners, we modeled many different pavement structures and also modeled the FWD load to account for the effect of temperature. We reflected this effect using the dynamic modulus as the table that I showed, and a temperature correction model was guessed. The Coefficients of this model was determined using nonlinear optimization based on nonlinear optimization using solver tool in Microsoft Excel. And then we used a road in Norway that was measured at 3 different temperature levels to validate our model. So here is the model that we recently developed for temperature correction of FWD data. In this model, DI is uncorrected deflection values, and DI core is corrected deflection values, and I is the radial distance. HAC is the thickness of the asphalt layer, and TPAVE is pavement temperature, which for thin asphalt layers can be approximated by surface temperature. And there are C1, C2, C3, C4 model parameters, and these model parameters were determined based on optimization for each radial distance. And these correction tables were developed. So we can see here, for example, for D0 at different asphalt layer thicknesses and different temperature levels, how much are these correction factors. As the reference temperature was considered 20 degrees of centigrade, so when temperature is 20, the correction factor is 1. When temperature is higher than 20 degrees of centigrade, so we will have higher deflection. So to adjust them to 20 degrees of centigrade, we need to apply correction factors that are generally lower than 1. And when temperature is lower than 20 degrees of centigrade, we certainly need to apply correction factors higher than 1 to adjust them to 20 degrees of centigrade. Also, we can see that by increasing the thickness of the asphalt layer, for example, for 8 degrees of centigrade, when asphalt layer thickness is 5 centimeter, this correction factor is 1.15, but it will increase to 1.24 at 25 centimeter asphalt layer thickness. And it is obvious that by increasing asphalt layer thickness, the viscoelastic component of the whole pavement structure will be more dominant. And this is the reason that these correction factors will be more influential. And also at high temperature levels for thin asphalt layers, we see that we have these correction factors, but at thicker asphalt layers, we will have more influential, more powerful correction factors. And the same were done for other radial distances. So this table can be applied for correcting D20 values and also for D30. And I have also shown some for outer radial distances, including D150 and D180. So if I just want to show one specific cell, so come back to this D0, we see that when temperature is 40 degrees of centigrade and asphalt layer thickness is 25 centimeter, the correction factor is 0.7 for D0. And for D20, it is 0.74. For D30 is 0.79. Here, 0.93. And at the last radial distance, it is 0.96. So the effect of temperature is more pronounced at inner radial distances. For D0 and D20, it is more influenced, it is more significant, but when asphalt layer thickness increases, it can also be influential on outer radial distances. If we put SCI values corrected using the same procedure, the developed model. So we correct D0 and D20 using the model and determine SCI 200 and also SCI 300 and put them on x-axis and use simulation to determine D0, D20, and D30 at reference temperature of 20 degrees of centigrade and put them on the y-axis. We see that after applying this correction model, the values can predict SCI values at reference temperature, as these points are mostly aligned along the line y equals to x, and also there are linear regression models with high coefficient of determination for both SCI 200 and SCI 300. These points were obtained based on modeling 1,000 cases in Ken layer, and we also included 100 additional cases using vScrew. And if we add these solid points into this curve, we see that again these points are aligned this line with high R squared values. And we also used the road in the Norwegian road network to validate our model. And as we see here, the coefficient of determination is pretty high, not as high as simulation cases, but in general, we can say that the model is working and the validation is done using this road section in Norway. Initial version of this work was presented in TRB 2026, and last month a journal paper from this work was published in Road Materials and Pavement Design. Here is the title, Introducing a Simulation-Based Model for Temperature Correction of Falling Wave Deflectometer Measurements. So if you are interested, you can find this paper and review it. But what happens for TSD? As I said, the principle is almost the same. But there are some specific differences. First, we cannot use the static load. We need to model a TSD load. So we need to use a software tool that is capable of modeling the moving load. So vScrew software was used. Second, we need to correct the effect of both temperature and speed, not only temperature. In FWD, the loading speed is not an issue, but here the vehicle speed is an issue and needs to be corrected. Reference conditions were considered 10 degrees of centigrade and 70 kilometers per hour. The reason that we considered the reference temperature of 10 degrees of centigrade was that we developed an index based on TSD data that could reflect the maximum horizontal strain at the bottom of the asphalt layer, and we wanted to compare this temperature correction with the temperature correction based on Swedish formula, which is originally at 10 degrees of centigrade. So this is the reason that here we consider this reference temperature, but based on this procedure, different reference temperatures can be defined and only the model parameters will change. Again, optimization was conducted using solver tool in Microsoft Excel. And in the validation phase, we are currently working on this part, a loop in Finland. We considered a loop in Finland, and we conducted TSD measurements at different temperature and speed levels. We are still working on analyzing data from this loop to see how can we use this loop for validating our model. So we developed a parameter known as fatigue strain index, which is determined based on deflection slopes, and developed this temperature and speed correction based for this fatigue strain index. So the shape is almost similar to FWD temperature correction by an important difference that a speed component has been added here. And the reason for adding this component is that based on literature, it is believed that 1 degree of centigrade increase in temperature has the same effect in TSD responses than 20 kilometers per hour decrease in speed. So for this reason, we used this component to incorporate both temperature and speed effect. But we are currently working on another correction factor. So this is something that I will show you the results based on simulation, but is not the most efficient one necessarily. And this temperature and speed correction was developed for this fatigue strain index, but can be expanded to SCI 200, SCI 300, and also deflection values and deflection slope values by different model parameters. So we need to repeat the optimization and find model parameters for the intended index that we want to correct the effect of temperature and speed for it. Here we can see a figure that shows fatigue strain index based on deflection slopes on the x-axis and the maximum tensile strain at the bottom of the asphalt layer obtained from software simulation in viscoroute for a limited number of simulated pavement structures. As we see, the R-squared value is high, and in general, we can say that this fatigue strain index is representing this maximum tensile strain or this critical fatigue strain. And if we apply the temperature and speed correction on this fatigue strain index and put it on the x-axis and determine maximum tensile strain at the bottom of the asphalt layer at reference conditions, 10 degrees of centigrade, 70 kilometers per hour, we see that the alignment is good. The R-squared value is pretty high. So this model is capable of correcting these fatigue strain values and reproduce corrected maximum tensile strain values. But as it is shown, it is based on a limited number of simulation cases, and also validation is required. The results of this study will be presented in the next BCRRA conference in Ljubljana, which will be held in 2 weeks. And the paper will also be published in Transportation Research Procedure. So if you are interested, you can check it when it is available. And if we apply this temperature and speed correction to the same road section that I showed in previous slides, we can see that when there is not any correction, there is no change between 2015 and 2020 measurements. But when we apply this temperature and speed correction, we see meaningful changes in deterioration over time. So this 2020 data is placed above this 2015 data, and we might be able to relate this change in SCI 200 values to deterioration patterns. But the problem is more complicated than this because this study shows that we need to correct temperature and speed effect, but it does not solve all the issues because there might be the influence of, for example, subgrade and moisture content in the subgrade and some other factors that need to be considered. For this reason, the validation part is very important in this study related to TST data. We recently conducted TST measurements on a loop near the border of Sweden, near the Tornio. So 4 road sections were considered in this these measurements. You can see more information about these sections. Road 927, 19552, 19553, and Road 21, which are representing 3 main road categories in the Finnish road network, were considered, and 6 measurement runs at 20 and 30 degrees of centigrade and 40, 60, and 80 kilometers per hour were conducted. So we are analyzing data from this loop to see how we can use it for validating our model. We may need to change some parts in our model. For example, we need to add some new simulation cases to represent the pavement structural conditions of this loop. So some corrections are needed, but after analyzing the data, after also completing the simulation parts, we will be able to see if we can use this loop for the validation of our model or not. So in general, TSTDs show a strong potential for network level structural evaluation of pavements, and compared to FWDs, they are faster, safer, provide more detailed and more cost-efficient assessment, not necessarily more accurate assessments, but they have some obvious advantages over FWDs. There are specific areas that need further development. For example, the topic of this study, which was developing temperature and speed correction factors for TSTD measurements and also validating them using field data. We need to develop specific structural indices for TSTDs and not to rely on FWD based indices. We need a specific back calculation methods, viscoelastic back calculation methods to estimate pavement layers modularly from TSTD data, and also standardized measurement protocol and quality control procedures to be sure that data from TSTDs are reliable. And there are also some open questions. For example, an interesting area for further investigation is there any correlation between TSTD data and rot depth progression? Rotting can occur at different pavement layers. So if we can separate the rotting at different layers, so those that's component that is related to rotting in sub-layers can be related to measurements from TSTD, but this is something that need to be investigated in future studies. This was my presentation. Thank you for your attention, and please let me know if you have any questions.